Welcome to this walkthrough of problem number 760, find anagram mappings. In this video, we'll break down the problem, explore different approaches, and walk through the solution step by step. Let's dive in. In this problem, we are given two integer arrays, nums1 and nums2, where nums2 is guaranteed to be an anagram of nums1. This means that nums2 contains the same elements as nums1, just potentially rearranged. Our objective is to return a mapping array such that mapping I represents the index of the element nums1 I in nums2. If there are multiple valid indices, any one of them can be returned. For example, if nums1 contains duplicates, and nums2 has those duplicates in different positions, we can choose any valid index for that element. The input constraints specify that nums1 and nums2 will have the same length, which will be between 1 and 100. Additionally, all elements in both arrays will be integers between 0 and 100,000. The goal is to compute this mapping efficiently while adhering to the problem's requirements. To illustrate this concept, let's look at the first example. Here, nums1 is 12, 28, 46, 32, 50, and nums2 is 50, 12, 32, 46, 28. The output mapping is 1, 4, 3, 2, 0. This means that nums1, 0, which is 12, is located at index 1 in nums2. Then, nums1, 1, which is 28, is at index 4 in nums2, and so on. For each element in nums1, we find its corresponding index in nums2 and construct the output array based on these indices. Since nums2 is an anagram of nums1, every element in nums1 will have at least one valid index in nums2, ensuring that we can always produce a valid mapping. Now, in the second example, nums1 is 40, 10, 20, 30, and nums2 is 10, 20, 30, 40. The output mapping is 3, 0, 1, 2. Here, nums1, 0, which is 40, is found at index 3 in nums2. Similarly, nums1, 1, which is 10, is at index 0 in nums2. For nums1, 2, the value 20 is at index 1, and for nums1, 3, the value 30 is at index 2. This shows how we traverse nums1 and identify the positions of its elements in nums2 to create the mapping array. In the third example, nums1 is 1, 2, 3, 4, and nums2 is 2, 4, 1, 3. The resulting mapping is 2, 0, 3, 1. For instance, the value 1 from nums1 is found at index 2 in nums2, 2 is at index 0, 3 is at index 3, and 4 is at index 1. The constraints for this problem ensure that nums1 and nums2 always have the same length, ranging from 1 to 100. Each array element is guaranteed to be between 0 and 100,000, and nums2 will always be an anagram of nums1. This guarantees that every element in nums1 can be found in nums2. There are also several edge cases to consider. For example, if nums1 and nums2 contain duplicate elements, the output can include any valid indices for those duplicates. If both arrays consist of the same single repeated element, like 1, 1, 1, the mapping can be any valid permutation of indices, such as 0, 1, 2. Lastly, when the arrays contain only one element, such as nums1 equals 7 and nums2 equals 7, the output will simply be 0. These considerations ensure that our solution handles all possible input scenarios appropriately. To solve this problem, we considered two main approaches. The first one is the brute force approach, which is quite straightforward. Here, for every element in nums1, we search for its matching index in nums2 using a nested loop. Since nums2 is guaranteed to be an anagram of nums1, we know that every element in nums1 has a corresponding element in nums2. However, this method is inefficient because for every element in nums1, we repeatedly scan through nums2, leading to a time complexity of n squared. This is manageable for small arrays but becomes impractical as the size of the arrays increases. To address this inefficiency, we can use an optimized approach involving a hash map. In this method, we pre-compute the indices of elements in nums2 and store them in a hash map. This allows us to retrieve the indices in constant time, significantly improving performance. By reducing the need for repeated scanning, we can handle larger arrays much more efficiently. Using a hash map offers key advantages over the brute force approach. First, it eliminates the need for repeated scanning of nums2, which is the main source of inefficiency in the nested loop method. Additionally, by storing the indices of each element in nums2 as lists, we can handle cases where nums2 contains duplicate values seamlessly. When we retrieve an index from the hash map, we simply remove it from the list to ensure that future lookups for the same value return the next available index. This approach achieves a time complexity of O(n), as we build the hash map in linear time and also perform lookups in linear time. The space complexity is also O(n), due to the storage required for the hash map. Given these efficiencies, the hash map approach is the most suitable for this problem, especially when working with larger datasets where performance is critical. When comparing the different approaches, each has its strengths and weaknesses. The brute force method is easy to implement and doesn't require any additional space, making it appealing for very small inputs or quick prototypes. However, it is highly inefficient for larger arrays due to its O(n)² time complexity. On the other hand, the hash map approach is much more efficient, with a time complexity of O(n). It naturally handles duplicates in nums2 and is scalable, though it does require additional space for storing the hash map. Another alternative is to use a sorting and binary search approach. This can work well if nums2 is sorted or can be sorted efficiently. However, sorting introduces an O(n log n) complexity, which isn't optimal for this problem, especially when nums2 is unsorted. Overall, the hash map approach strikes the best balance between time and space efficiency, making it the most practical solution for solving this problem effectively. To solve the problem of finding the indices of elements in one list within another, we can start by understanding the inputs and outputs. We have two lists, nums1 and nums2. Our goal is to determine the index of each element in nums1 as it appears in nums2. If an element in nums1 doesn't exist in nums2, the output should indicate this with a -1. The brute force solution involves two loops, an outer loop to iterate through each element in nums1, and an inner loop to traverse nums2 to locate the first occurrence of the current element. This process ensures that we systematically search for each element in the second list, though it may not be the most efficient method for larger inputs. To implement the brute force approach, we start by creating an empty list called result to store the indices. For each element in nums1, we use a loop to iterate over all indices of nums2. During this traversal, we check if the current element in nums2 matches the current element from nums1. If a match is found, we append the index of this match to the result list and exit the inner loop. If the inner loop finishes without finding a match, we append -1 to the result list to indicate the absence of that element in nums2. Once all elements in nums1 have been processed, we return the result list. Additionally, we need to handle some edge cases, such as when nums1 is empty, in which case we return an empty list, or when nums2 is empty, where we return a list of -1s for every element in nums1. This brute force solution relies on a nested loop structure, where the outer loop goes through each element of nums1, and the inner loop compares it with every element in nums2. While this ensures that all matches are found, it comes at a cost. The time complexity is O(n*(m), where n is the size of nums1 and m is the size of nums2, because for each element in nums1, we potentially iterate through the entire nums2. On the other hand, the space complexity is relatively low, at O(n), since the only additional space required is for the result list. However, this approach becomes inefficient as the input sizes grow, making it unsuitable for scenarios where performance is critical. To address this limitation, more optimized solutions, such as those using hash maps, can be considered. The brute force approach primarily uses a list as the core data structure to store the indices of elements in nums1 as they appear in nums2. This keeps the solution simple and straightforward, with no additional data structures needed. The algorithm relies on three key operations. First, the outer loop iterates through each element of nums1, ensuring that every element is processed exactly once. Second, the inner loop searches for the current element from nums1 within nums2, ensuring we locate the first occurrence if it exists. Finally, the comparison operation between elements in nums1 and nums2 ensures that matches are accurately identified, while appending -1 accounts for elements that are missing in nums2. These operations are fundamental to the brute force solution, even though the overall efficiency can be a concern. Updating the result list is a critical step in maintaining the correctness of the output. Each time a match is found, the index is appended to the list, ensuring that the output maintains the same order as the elements in nums1. For elements that do not exist in nums2, appending -1 ensures that the absence is represented accurately. This systematic update of the result list guarantees that the algorithm produces the correct output for all inputs, regardless of edge cases or the order of elements. While this approach is straightforward to implement, its inefficiency highlights the need to explore optimized solutions for larger datasets. This implementation efficiently solves the find anagram mappings problem. The function anagram mappings takes two lists, nums1 and nums2. The goal is to map each element in nums1 to its corresponding index in nums2. First, we construct a dictionary called index_map to store the indices of all elements in nums2. This is done using a simple for loop, where we enumerate through nums2 and map each element to its index. This pre-processing step ensures we can find the index of any element in nums2 in constant time, O1. Next, we use a list comprehension to iterate through each element in nums1. For every element in nums1, we look up its index from the index_map dictionary. Since dictionary lookups are O1, this step is very efficient. The overall time complexity of this solution is O, n plus m, where n is the length of nums2 and m is the length of nums1. This is because we process nums2 once to build the dictionary, and then iterate through nums1 to construct the result. The space complexity is O, n, due to the storage of the index_map dictionary. This approach is optimal and handles edge cases, such as repeated elements in nums1 and nums2, correctly because the problem guarantees that nums1 is an anagram of nums2. This is the Java implementation of the find anagram mappings problem. The logic mirrors the Python solution but uses Java-specific collections such as hashmap to store the indices of elements in nums2. The result array is built by mapping each element in nums1 to its corresponding index in nums2. Key differences include Java's explicit type declarations and the use of arrays instead of Python lists. To solve this problem, we start with the first example where nums1 is given as 12, 28, 46, 32, 50, and nums2 is 50, 12, 32, 46, 28. The task requires us to find the mapping of indices from nums2 that correspond to the elements in nums1. First, we initialize an empty dictionary called index_map, which will help us store the indices of each element in nums2. We then loop through nums2 using the enumerate function. For each element in nums2, we add it to the index_map dictionary along with its corresponding index. For instance, when the element is 50 at index 0, we add 50, 0 to the dictionary. Similarly, for 12 at index 1, we add 12, 1, and so on. By the end of this process, index_map contains all the elements of nums2 as keys and their indices as values. The final dictionary looks like this: 50, 0, 12, 1, 32, 2, 46, 3, 28, 4. This map will allow us to quickly retrieve the index of any element in nums2. Now that we have the index_map ready, we can determine the indices that map nums1 to nums2. To do this, we loop through each element in nums1 and use the index_map dictionary to look up its corresponding index in nums2. For example, the first element in nums1 is 12, and looking it up in index_map gives us 1. Similarly, for 28, we get 4, for 46, we get 3, then for 32, we get 2, and finally for 50, we get 0. As we collect each mapped index, we form the result array, which becomes 1, 4, 3, 2, 0. This array represents the indices in nums2 that correspond to the elements in nums1. The final output for this example is 1, 4, 3, 2, 0. In the second example, we deal with repeated elements. Here nums1 is 1, 2, 1, 3, and nums2 is 3, 1, 2, 1. We start by initializing an empty index_map dictionary. As we build the index_map by iterating through nums2, we first add 3 o'clock for the element 3 at index 0. Then for the first occurrence of 1 at index 1, we add 1, 1. For the element 2 at index 2, we add 2, 2. When we encounter the second occurrence of 1 at index 3, we update the existing entry for 1 to 1, 3 since we always overwrite with the latest index. By the end of this step, index_map becomes 3 o'clock, 1, 3, 2, 2. This map now reflects the updated indices for nums2, including handling duplicates by keeping the most recent occurrence. Using the updated index_map, we now find the indices that map nums1 to nums2. For the first element in nums1, which is 1, we look up index_map and find its index is 3. The next element, 2, maps to 2. For the second occurrence of 1 in nums1, we again find its index is 3 because index_map stores the latest occurrence. Finally, for the element 3, the mapped index is 0. Collecting these indices gives us the result array 3, 2, 3, 0. This output reflects the correct mapping of nums1 to nums2 while handling repeated elements effectively. The final output for this example is 3, 2, 3, 0. In the third example, we encounter an edge case where nums1 and nums2 are identical, given as 4, 9, 7. To solve this, we begin with an empty index_map dictionary. Iterating through nums2, we add 4 o'clock for the first element 4 at index 0, then 9, 1 for the next element 9 at index 1, and finally 7, 2 for the last element 7 at index 2. Since there are no duplicate elements in this example, the index_map remains straightforward and ends up as 4 o'clock, 9, 1, 7, 2. This map captures the indices of all elements in nums2 exactly as they appear. Finally, we use the index_map to map the indices from nums1 to nums2. For the first element in nums1, which is 4, we find its index is 0. Similarly, for the next element 9, we get 1, and for the last element 7, we get 2. Collecting these indices forms the result array 0, 1, 2. Since nums1 and nums2 are identical in this example, the mapping directly reflects their order. The final output for this case is 0, 1, 2, which confirms that the solution works seamlessly even when nums1 and nums2 are the same. To determine the time complexity of our algorithm for solving the find anagram mappings problem, we break it into 2 key steps. First, we build the index_map dictionary by iterating over nums2 using a for loop with enumerate. This allows us to map each element of nums2 to its corresponding index. Since this process involves visiting each element of nums2 exactly once, it takes m time, where m is the length of nums2. Next, we construct the result list by iterating through each element in nums1 and using the index_map for constant time lookups. These lookups are 1 on average, and since we perform n lookups, 1 for each element in nums1, this step takes n time. Combining these 2 steps, the overall time complexity of the algorithm becomes m plus n, as the operations are sequential. Now, examining the space complexity, the algorithm requires additional memory for 2 structures, the index_map dictionary and the result list. The index_map stores 1 key value pair for every unique element in nums2. In the worst case, where all elements of nums2 are unique, the space required is m, with m being the length of nums2. The result list, on the other hand, stores 1 entry for every element in nums1. This results in a space requirement of n, where n is the length of nums1. Adding these together, the total space complexity of the algorithm is m plus n, which accounts for the memory used by both the dictionary and the result list. Let's compare this optimized approach to a brute force solution. In a brute force method, for each element in nums1, we would scan the entire nums2 to find its index. This nested loop logic leads to a time complexity of n*m, as every element in nums1 performs a complete traversal of nums2. However, the brute force approach does not require additional data structures, so its space complexity is 1. In contrast, the optimized approach significantly reduces the time complexity to m plus n by using a hash map for efficient lookups. The trade-off is an increase in space complexity to m plus n, due to the memory needed for the dictionary and result list. Overall, this makes the optimized solution much more efficient for larger input sizes. Finally, let's analyze the best, average, and worst-case scenarios. Regardless of the case, the time complexity remains m plus n. This is because both building the dictionary and constructing the result list involve fully iterating through their respective inputs, making the operations independent of the data distribution. The hash map lookups, which are 1 on average, ensure that constructing the result list is efficient. In the worst case, where all elements in nums2 are unique, the dictionary grows to m in size, but the overall complexity remains m plus n. Mathematically, the time complexity is derived by summing O, M, for dictionary creation and O, N, for result list construction, resulting in O, M plus N. This linear complexity highlights the efficiency of the optimized approach, especially when compared to the brute force method, making it well suited for handling large inputs. When solving this problem, there are a few common mistakes to watch out for. First, ignoring edge cases can lead to runtime errors or incorrect results. For example, if either nums1 or nums2 is empty, the solution might break. To address this, always test edge cases like empty arrays, single-element arrays, or cases where the two arrays have no overlapping elements. Next, relying on inefficient nested loops can drastically increase the time complexity to O, n squared, which isn't feasible for larger inputs. Instead, consider optimized approaches like using hash maps or binary search. Additionally, handling indices incorrectly is another frequent issue. Mistakes in keeping track of indices during lookups can lead to off-by-one errors or mismatches. Be meticulous with index management and double-check your results against expected outputs to avoid these pitfalls. Another mistake to avoid is assuming that nums2 is sorted, unless the problem explicitly guarantees it. Building your logic around this incorrect assumption can lead to flawed solutions. If sorting is necessary, make sure to sort the data explicitly or adapt your algorithm to handle unsorted input. Overcomplicating the solution is also something to be cautious of. Introducing unnecessary complexity, like additional data structures or redundant steps, can increase space usage and make debugging harder. Aim for a clear and simple solution, ensuring that every step is both necessary and efficient. By staying mindful of these common mistakes, you can develop cleaner, more robust solutions. For interviews, there are some key insights that can help you stand out. First, hash maps are often the optimal choice when working with problems that involve lookups and indexing. They offer an average time complexity of O(1) for insertions and lookups, which makes them highly effective. Binary search, on the other hand, is a great option when nums2 is sorted, as it allows for O log n lookups. Just be sure to confirm whether sorting the input is allowed within the problem's constraints. It's also important to communicate trade-offs during the interview. For instance, hash maps require extra space but significantly reduce time complexity, while sorting modifies the input but enables binary search. Finally, practice verbalizing edge cases and walking through your code with examples. Explaining your thought process clearly demonstrates a strong understanding of the problem and builds confidence with interviewers. To further build your understanding, you can explore related problems that use similar techniques. For example, LeetCode 1.2 Sum focuses on using hash maps to efficiently find pairs of elements that meet a specific condition. LeetCode 350, Intersection of Two Arrays 2, involves comparing elements between two arrays, requiring similar logic. LeetCode 4, Median of Two Sorted Arrays, is a more advanced problem that demands efficient searching in two arrays. And LeetCode 49, Group Anagrams, highlights the power of hash maps for grouping elements efficiently. As for alternative approaches, the brute force solution is straightforward but inefficient. With a time complexity of O, n squared, and space complexity of O(1), it's simple to implement but unsuitable for larger inputs due to its slow performance. The hash map approach is a much more efficient alternative. It provides a time complexity of O, n plus m, and a space complexity of O, n. This method is widely applicable and balances efficiency with ease of implementation, though it does require additional space to store the map. Another effective option is the binary search approach, which, assuming nums2 is sorted, achieves a time complexity of O, n log m, and a space complexity of O(1). However, if nums2 isn't already sorted, you'll need to account for the pre-processing time of O, m log m, to sort it. Each of these approaches comes with its own trade-offs, so understanding when to use each one is key to solving problems optimally. Thanks for staying with us through this problem walkthrough. To recap, we used a hash map for efficient lookups, achieving an optimal solution. Remember, mastering hash maps is key for similar problems. If you enjoyed this, don't forget to like, share, and subscribe for more content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!